So we're ready to build up a hypothesis test. Let's look at this one. A researcher obtains a simple random sample of 1,000 people and finds that 534 are in favor of banning the cell phone while driving. Thus, p hat, the sample proportion, is 534 divided by 1,000. Does this suggest that more than 50% of people favor the policy? Well, let's talk about that. 534 out of 1,000 people favor changing the policy on cell phone use while driving, banning it. Does this suggest that more than 50% of people favor changing it, the policy? Well, on the surface it does, because that's more than half the sample, but remember, that's not the end-all be-all. How good is the sample a representation of the underlying population? Well, that's why we need confidence intervals for something like that. We simply need to start by considering what our hypotheses are. We want to know if more than 50% of people favor changing the policy. So this must be a right-tailed test. The population proportion greater than 0.5, that is what we're testing. This could also be called your P0. It's the hypothesized value of the proportion. You can call it that if you want, but I won't use that terminology quite here. So we have our hypothesis set up. This is thus a right-tailed test. We need a test statistic. If you recall, we went over this test statistic last time. It's this business down here. P hat minus P0 divided by the square root of P0 times 1 minus P0 over N. So P hat, which is 534 over 1,000, is 0.534. Let's use the classical approach. Let's find the critical value. Let's assume a level of 0.05 for the test. So what's happening in this right-tailed test? Here is your normal distribution curve, your bell curve, whatever. And I'd be remiss if I didn't fix that a little bit. There we go. What we're looking for is whatever Z value has 0.05 of the data, which is the level of the test, to the right of it. So we're going to have to use a Z chart. Which is something we should be comfortable with at this juncture. And let's see, if 0.05 is to the right of it, that means 0.95 is to the left of it. That's going to be a Z value of 1.645. I'll use red. So the bottom line, we will calculate our test statistic. If it is greater than z equals 1.645, we reject the null. Otherwise, we don't. So this, in a right-tailed test, this critical value is the largest will allow a z value. Any larger than that, and we have to reject the null hypothesis. All right. So what we're going to do, we're going to calculate the test statistic here. That's going to be 0.534 minus 0.5 all over the square root of 0.5 times 1 minus 0.5 all over 1,000 inside the square root. Now we can bust out a calculator. We're going to get, if you do this slowly, give myself a little more space. 0.034 on top. On bottom, you'll get about 0.0158. Which will give you 2.152. So our conclusion our test statistic of 2.152 is greater than 1.645, the critical value. Thus, we reject the null hypothesis. There is enough evidence to suggest that the true proportion of those who want to change the policy is greater than 50%. That's kind of what we're rolling with here. That is what we are rolling with. So we just ran a hypothesis test for a proportion. It was a right-tailed test. Yay. Now we are also capable of talking about the p-value approach. The p-value is the probability of obtaining a test statistic that is at least as extreme as what you've found. If you calculate a high p-value, then your null hypothesis, your data are likely under the null hypothesis. Thus, a high p-value supports the null hypothesis. A small p-value, though, suggests that your data are incompatible or unlikely under the null hypothesis. Thus, a small p-value is bad for the null. So there's the saying, if the p-value is low, the null must go. So we won't get into the nitty-gritty per se. You can look at it for a left-tailed test. So let's zoom in on this. Let's talk about a left-tailed test. You first calculate your test statistic after doing everything else in the test. Now let's say that this is your test statistic. That you've calculated. On a left-tailed test, the p-value will be the area under the curve to the left of it. In other words, your p-value is the probability of being to the left of your test statistic. That's how you calculate your p-value. Then, if your p-value is less than the level of your test, you reject the null. Otherwise, you don't reject. Now that's great for a left-tailed test, so it's the probability being less than your test statistic, which you can use a z-chart to find. For a right-tailed test, after setting everything up, calculate your test statistic. Let's say this is your test statistic, z naught. Now the p-value is going to be this area right here. This is your p-value, not your O value, your p-value. Thus, your p-value equals the probability of being greater than your test statistic. So a right-tailed test, it's the area to the right of your test statistic. Then if your p-value is less than the level of your test, you reject the null hypothesis. Otherwise, you don't. No matter what, you always, if you have too small of a p-value, you reject the null hypothesis. Large p-value, you fail to reject the null hypothesis. And you compare it against the level of the test, which is alpha. Finally, for a two-tailed test, set everything up, then calculate your test statistic. But now there's a twist. Whatever your test statistic is, it's going to have a cousin that's the negative of it, or vice versa. Now the p-value this is half the p-value, this area. This is also half the p-value, this area. So to find the p-value, you need to find the area in one of the tails and double it. Because you need both of them to be added together. And there's symmetry, so you can just double it. Then if your p-value is less than the level of the test, you reject the null hypothesis. Otherwise, you don't. So that's kind of interesting that we have this formulation for it. That we can look at it depending on the type of test you have. So it's really important to remember that. So in a Gallup poll, a random sample of 805 adults were asked to identify their favorite seat when they fly. 442 indicated that it was a window seat. At a 0.05 level of significance, test the claim that the majority of adults prefer a window seat when they fly. But a majority of adults, so more than 50%. Now that would make this a right-tailed test. We already ran a right-tailed test. So let's actually skip over that one. We're not going to look at the confidence interval approach. Let's change this one up a little bit so we can work it. Let's say instead of that a majority of adults will prefer a window seat, we'll say that the proportion of adults who prefer a window seat is different from 0.6. So I'll take care of that. Let me share the screen. We'll change it up just a little bit, just enough to make it interesting. So let's say 442 out of 805 people surveyed prefer a window seat. At the 0.05 level, test the claim that the proportion of people who prefer a window seat is not 60%. That's a good one. Well, I don't care who you are on this planet or planet Krypton, which is no more. You're going to want to, whenever you're doing a hypothesis test, you're going to want to set up your null and alternative hypotheses. So let's do that. The null hypothesis, the alternative, in this case, the claim is that the proportion of people who prefer a window seat is not 60%. So let's just set up the alternative real quick. The alternative is that the proportion of people who prefer a window seat is not 60%, which is 0.6 written as a proportion. Thus, no matter what, the null has to be that it is equal to 0.6 because there's only three types of tests: a right-tailed test, a left-tailed test, a two-tailed test. This must be a two-tailed test just because of the wording. the alternative hypothesis pretty much gives it away. Now this is going to be your P0, if you think about it, in your test statistic calculation. So calculate test statistic. Well, it's going to be P hat. So we need to get what P hat is, kind of as a preamble to this. P hat is going to be the proportion of the sample that prefers a window seat. So P hat is going to be 442 out of 805. That's how we incorporate that sample information. Popping that into a calculator, you're going to get 0.549. Now, remembering the test statistic formula here, P hat minus P naught, the hypothesized value of the proportion, which means it's going to go negative, which is totally fine, divided by the square root of all this business. Let me write it a little better than that. Divided by 805. That's all inside the square root. The numerator is negative 0.051. The denominator is something I will tell you in just a moment here. The denominator is going to be 0.173. And so our test statistic value is going to be negative 2.95. So we're going to calculate a p-value. It's going to be twice the probability of getting a z-score less than negative 2.95. Because the probability of being less than negative 2.95 is the area in one of the tails, and then we're doubling it because of it's a two-tailed test. So that's going to be equal to, pulling up a z-chart, looking up 2.95, that's going to be 0.0016 is the area in that tail. So our p-value is very small. The p-value is less than the level of the test, way less, so we reject the null hypothesis. There is enough evidence to support the idea that the true proportion of people that don't prefer a Windows or that prefer a window seat is different from 0.6. That's all we're saying. We're just saying, hey, we rejected the null, thus we went with the alternative hypothesis. The alternative hypothesis kind of won out here because our p-value was so low. And thus, we are supporting the idea that the null hypothesis is not true. We're rejecting it. We're supporting the alternative hypothesis, which says that the true proportion is not 0.6. So we've ran another hypothesis test, this time using the p-value. Now, we've talked about a hypothesis test for a proportion. One last thing, there's something called the confidence interval approach. All you do is go back to chapter 9, you just build up a confidence interval. If the hypothesized value of your proportion is in the confidence interval, that means the null hypothesis looks really good. So you failed to reject the null. However, if the hypothesized value of the proportion is not in the confidence interval you create, the chapter 9 confidence interval, then we're going to reject the null hypothesis. So pretty straightforward. Now we're going to test for a population mean. We're going to test for the average value of a population as opposed to the proportion. So we can use the classical approach, except that we must use a t-table instead of a z-table, because it turns out that in order to test the mean, we have to use the t distribution instead of the z distribution. That's going to change our test statistic into something that looks like this. So remember some quick properties about the t distribution. You need to know degrees of freedom. It's very similar to the normal. It looks kind of like a bell curve. We can use, we're just going to have to use the t-test for testing a hypothesis about a population. So the classical approach, which is actually going to be the only approach that we can really look at, the classical approach will have us, again, determining our hypotheses. We need to determine if it's a two-tailed test, a left-tailed test, or a right-tailed test. We select a level of significance alpha based on how seriously we want to not make a type 1 error. We're going to have a test statistic. It's going to be a t statistic. So we use t0 here. It's going to be x bar, the sample mean, minus mu naught, which is going to be the hypothesized value of the population mean. On bottom, we have to do S, the sample standard deviation, divided by the square root of the sample size. We're then going to say that this is a t-distributed variable with n-1 degrees of freedom. And then we need to use the t-table to figure out the critical region of interest. If the test statistic falls in the critical region, we reject the null hypothesis. If the test statistic does not fall in the critical region, we do not reject the null hypothesis. And then finally, we state the conclusion. Either we reject the null and have enough evidence to support the alternative hypothesis, or we fail to reject the null and say we don't have enough evidence to support the alternative hypothesis. So playing around with it, let's pull up what a t-chart would look like. Let's do that. And we'll work this together. So it says, for a right-tailed test with 15 degrees of freedom, find the critical t-value given that the level of significance is alpha equals 0.05. So what we're looking for, I'll zoom in a little bit here. We're looking in this case for the t-value that has 0.05 of the data to the right. That's going to be our critical value here. There's going to be 15 degrees of freedom. So if we come here and look at this chart, it tells us the area in the right tail. We want to look at 0.05, so we want to look at this column. We want the area in the right tail to be 0.05, so we are limited to what levels of significance we can choose. We can't choose a level of significance of 0.9 because 0.9 is not on this chart. So we are limited, but that's okay. Technology can deliver us more results. And then we want 15 degrees of freedom, which I'll make it really cool here. 15 degrees of freedom. Oh, that's this row. And so, aha, here's our culprit, the one that's up there. So 1.753 is our critical value in this right-tailed test. Oops, wrong thing. $1.753. Now our critical value, let's look at another example, a left-tailed test. So now we're looking to the left. Whatever this is the critical value. And we're going to want, in this case, 0.01. to be in that region. But Josh, the chart only gives me right-tailed. It only tells me areas to the right. That's okay. It's going to be symmetric. We're going to have a sample size of 20. So the degrees of freedom, which is n minus 1, is 19 degrees of freedom. So back to the chart, we're looking at 19 degrees of freedom against an area in the tail of 0.01. So that's going to be our guy, except that's the area in the right tail. So the test statistic value, or the critical value, is positive. Here, it's going to have to be negative. So negative 2.539. Because we want the area in the left tail. The bell curve, the T-bell curve, is symmetric about 0. So if you want any T values down here, they got to be negative. T values up here would be positive, but T values down here would be negative. Sorry, let me show you what I'm seeing. Zero. So any T values down here would have to be negative, which is what we want. We wanted this region and we wanted this T value right here. So our critical value is negative 2. What did we get? 2.539. Finally, for a two-tailed test with 15 degrees of freedom, your critical value, well, it's split up into two places. Here's the positive T value, but here's the negative T value corresponding to it. And then the 0.05 level of significance has to get divided up into two pieces. To get divided up into two different pieces. Then we'll go look at our chart. Now, even though our significance was 0.05, we want to look along the 0.025. We want to look along here at 15 degrees of freedom. So that's 2.131. So 2.131. And that's what we're going to have. Negative 2.131, positive 2.131. So a test statistic value that is less than negative 2.131 or greater than positive 2.131, it's in one of these tails, that is going to be where we reject the null hypothesis. So let's do a whole test. Together. Assume that the resting metabolic rate of healthy males is 5710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found that their resting metabolic rate was 5706 with a standard deviation of 14. So, at the 0.05 level of significance, is there evidence to conclude that the mean is different from 5710? So setting up our hypotheses, the null and alternative, the alternative, we want to know if it's different from 5710. So this is automatically going to be a two-tailed test. The null then has to be that mu equals 5710. Notice we're using mu now. So this must be two-tailed. The level of the test is 0.05. Now, if the level of the test is 0.05, that means that half of that has to be in the lower tail and half of that has to be in the upper tail. That's how we're going to find our critical values. So 0.025 is up there, 0.025 is down there in the tail. We're going to go to our T-chart. We're going to look at, there's a sample size of 45. So we're going to look at 44 degrees of freedom. Well, some T-charts will have exactly that much. Some you're going to have to get kind of a ballpark. So we're going to say it's about 2.019. So 2.019 for 44 degrees of freedom had 0.025 of the data to the right of it. Thus, this is negative 2.019. So the way it works is if I calculate my test statistic and it falls between negative 2.019 and positive 2.019, I'm going to fail to reject the null hypothesis because anything here in the white region is normal under the null hypothesis. But if it's less than negative 2.019 or greater than positive 2.019, I'm going to reject. So the test statistic is going to be, well, the sample had a mean of 5706. The hypothesized value is 5710, so we're going to have a negative number on top. Over, the standard deviation was 14 over the square root of 45. This is going to be our test statistic calculation. And if you do that, you'll get negative 4 on top. 14 over the square root of 45 is about 2.086 in some other business. So you're going to get negative 1.92 as your test statistic value. Now that's a fairly extreme test statistic, but it's not extreme enough. The test statistic was not in the rejection region because it was in between negative 2.019 and positive 2.019. Thus, we fail to reject the null hypothesis there is not enough evidence to suggest that the mean is different from 5710. That's our conclusion. But it was close. Negative 1.92 was really close to being in the rejection region, but wasn't quite. It was like right here. So it was just barely inside the white region in between those two critical values. Okay, let's take attendance real quick, and then I will see you all bright and early Monday morning